In this video, you'll learn about motion maps. Motion maps are a way of representing the position as a function of time of an object, and from that you can deduce the velocity as well. So for instance, let's say we have a car moving from left to right at a constant speed. We would indicate the first second or the first moment in time in which we care about this car using a dot, a simple dot. Then what we would do is we would represent each subsequent second, but we have to indicate the direction that the car is going first. So what I would do is draw an arrow, a vector if you will, representing the car's motion to the right. Now I also want to indicate roughly how fast the car is going. Because this car is moving at a constant speed, all the arrows that I draw will be the same size. But in cases where the car is speeding up and slowing down, you would be able to see how fast the object is moving at one point relative to another point. So in this case, I want to continue drawing dots at each second. So let's say at each second I see the car in its position as is indicated on the picture, the figure. So there are my 4 seconds worth of travel from beginning to end, or actually 3 seconds. Elapsed time. And so because the car is moving at a constant velocity, again, I'm going to draw similarly sized vectors, each to the right, for this car. Notice that there's space between my dots and my vectors, and that is essentially just an aesthetic tool that I use to make my motion map understandable. If the car were moving faster from left to right, and I'm looking at it in the same window that I was looking at the previous car, you would know that you would see the car fewer times. So in this case, I only see the car 3 times as it passes through my window. And this indicates that at every second I have seen the car. So I'm going to draw my dots to represent the position of the car over those 2 elapsed seconds from beginning to end. And in this case, unlike the previous case, my arrows are going to be much larger, indicating the car is moving much faster. Now if the car were moving to the left, we know that we need to keep track of that direction because we are working with vectors here. Let's say it's going the same speed, but just the opposite direction. So we were seeing that car 3 times moving from left to right. We're also going to see it 3 times moving from right to left. And so the lengths of my vectors should roughly be the same as they were in the previous problem, but pointing to the left. We can use motion maps to assist us in drawing position versus time graphs for an object. So for instance, we have a slightly more complicated example here. A car that we start analyzing, let's say it has a stroboscope on it, or some sort of periodically illuminating light. Maybe somebody's clicking a flashlight on every second. And we see it start at 0 seconds and it's moving quickly to the right. At 1 second it's still moving quickly to the right, and at 2 seconds it's still moving quickly to the right. But at 3 seconds it's no longer moving. Well, if it's moving very quickly to the right, we would know that its position would be increasing at a very large rate. So up to 3 seconds, the car moves through a very large position. And I'm going to start and assume that the car started at 0 position. And at each second, it seems to be traveling the same distance or covering the same position that it did every second previous. So I can connect that line, suggest that the car is moving very quickly. From 3 to 5 seconds, the car is not moving at all, according to the motion map, and so therefore the position should not change. So at 4 seconds and 5 seconds, we should have a constant position. And then 5, 6, 7, 8, and 9 seconds, where we finally cut off our analysis, it seems that the car is not moving quite as quickly. And so in this case, its position change is not going to be as great as it was in the first segment, the first 3 seconds of travel. And so it looks like the car is going to end up at about the same position it was at 1 second. And so I'm going to put 9 seconds, there's my dot, and I know that it's going to be doing that at a constant rate, and so therefore there is my graph of the motion map. Notice that each of the points in my motion map corresponds to a point on my graph itself. And even though I haven't drawn each and every point in here, you can convince yourself that each of these motion map points would have a corresponding point on the graph. So here's a case where we have two cyclists, cyclist A and cyclist B, and when the scene begins, we see a flashlight from B illuminating B and a flashlight from A illuminating A, and it seems like A is to the right of B. And if we're calling to the right a positive direction, which it seems that we are in this example, then we would say A starts at a position more positive than B does. Right. 1 second into it, B is now at A's original position, it appears, but A has now moved ahead of that, so B has not quite caught A. So it appears that those points exist to a certain extent. There we are, 1 second after the scene begins. We can continue with this method 2 seconds after the scene begins. A is now moved a little bit further. B has moved a little bit further as well. And you can see that actually B, at 2 seconds, is getting much closer to A. And so you can see here at the pivotal point, 3 seconds into this analysis, the motion map tells us they're actually at the same position. That corresponds to the intersection of the graphs. So there's a lot that we can see graphically, even if we don't have a motion map. But at the very least, we should be able to draw graphs from our motion map. A few quick hints on drawing your motion maps. Remember to draw the dots for every second or equal time interval that exists. Typically, it's going to be seconds for us. Then attach arrows or vectors to the dots indicating the direction of motion, and make sure they're, relatively speaking, preserving the value of the speed of the object. So a long arrow for a high speed, a small arrow for a low speed. If an object stops, you want to draw multiple dots. You don't want to condense 3 seconds of stopped motion into one dot. Otherwise, we lose all concept of time. So make sure you have a dot drawn for every second of time, even if an object isn't moving. And then make sure your sequence of arrows has a logical flow, so motion's clearly communicated. In essence, make sure they're pointing to the left if it's going to the left, to the right if the object's going to the right, and try not to bump them into each other.